Did you know that time actually travels faster on Mars than it does here on Earth? This fascinating phenomenon is a direct consequence of Albert Einstein's theory of general relativity, where clocks on Mars tick at a slightly different rate. Specifically, this difference is due to time dilation effects, a concept where time itself can speed up or slow down. These effects are influenced by both gravitational fields and the relative orbital velocities of celestial bodies. On average, clocks on Mars tick a remarkable 477 microseconds faster per day compared to clocks here on Earth. This subtle discrepancy accumulates over time, highlighting constant variations in space-time. This subtle yet significant discrepancy arises from multiple factors, primarily Mars' weaker gravitational pull. This weaker gravity directly impacts how time is experienced on the red planet. Mars' surface gravity is 5 times weaker than Earth's. This substantial difference directly translates to less gravitational time dilation on the red planet. Another key factor is Mars' orbit around the Sun. It orbits at a slower average speed because it is farther out, at about $1.52 compared to Earth's $1. While a slower orbital speed would typically make time pass slower, Mars' orbit is not perfectly circular. Its more eccentric orbit introduces significant variations in its speed, affecting the rate at which time passes. Mars' orbital speed varies dramatically throughout its journey around the Sun. It moves faster when closer to the Sun at perihelion, around $1.38, and slower when farther at aphelion, about $1.67. Gravitational influences from the Sun, Earth, and Moon also play a complex role. These forces constantly vary as Mars progresses through its 687 Earth-day orbit, subtly affecting its trajectory and the passage of time. Scientists Neil Ashby and Baidyanath Patla from the National Institute of Standards and Technology, or NIST, meticulously calculated these effects. NIST is a renowned authority in measurement science, ensuring the precision of their findings. They used a complex four-body problem model involving the Sun, Earth, Moon, and Mars to determine the precise time dilation. This sophisticated simulation accounted for all gravitational interactions. Baidyanath Patla noted the immense computational challenges involved, calling it heavy lifting. He emphasized that a three-body problem is already extremely complicated, making a four-body problem significantly more arduous. The average 477 microseconds per day difference is not static. It fluctuates by up to plus or minus 226 microseconds, depending on Mars' orbital position relative to Earth and the Moon. This variation depends on Mars' orbital position relative to Earth and the Moon. Its precise location dictates the strength of gravitational forces, influencing the exact rate of time dilation. For context, this is the same relativistic effect behind the famous twin paradox. This thought experiment illustrates how time can pass differently for individuals in varying frames of reference. A twin traveling near light speed would age slower than their sibling who remained on Earth. This is a direct consequence of special relativity, where time passes more slowly for the fast-moving twin. Near black holes, extreme gravitational forces are so immense that they cause time itself to slow down dramatically. This showcases the profound impact of these incredibly massive cosmic objects on space-time. Even on our own moon, clocks run 56 microseconds faster per day than on Earth. This is a testament to the moon's weaker gravitational field compared to our planet. These differences, though tiny, are incredibly important for future Mars missions. Accurate time synchronization is paramount for complex interplanetary endeavors and successful operations. Navigation systems like GPS rely on incredibly precise atomic clocks to function accurately. Relativistic effects on these satellite clocks are already meticulously calculated and corrected for on Earth. For instance, GPS satellites run approximately 38 microseconds faster per day. Without constant adjustment, these clocks would quickly become inaccurate, leading to significant navigation errors. For future Mars networks, precise synchronization will be absolutely crucial. Advanced technologies like 5G demand astonishing accuracy, requiring synchronization within a mere 0.1 microseconds for optimal performance. Uncorrected time dilation could have severe consequences for Mars missions. It could disrupt critical communication links and severely impair rover navigation across the inner solar system. Neil Ashby emphasized the proactive importance of studying these complex relativistic issues now. This research is vital, even if it takes many decades before Mars is extensively covered by rover tracks. Ashby stated that future navigation systems on other planets and moons will depend on accurate clocks. Einstein's general theory of relativity provides the essential framework for precisely analyzing and predicting these critical clock rates. Baijanaf Patla added that the current era is just right for focusing on the Moon and Mars. We are closer than ever to realizing the science fiction vision of expanding across the solar system.